All right, in this video we want to talk about surface area. Now, surface area in general is a little tricky to calculate. It actually will happen in Calc 4 when we do some more calculations of parametric surfaces. But for now, there's one group of surfaces that we can find the surface area of reasonably easily, and those are what are called surfaces of revolution. We've already done volumes of revolution. Now we want to look at surfaces of revolution. So one thing to be careful of here is that the pictures are going to look a lot like the pictures of when we were calculating some volumes, but we're looking at different things now. I'm going to start with some function, some graph of some function, y equals f of x, starting at some a value and ending at some b value. And then I'm going to rotate this curve around an axis, either the x-axis, the y-axis, or some other axis for that matter. Let's, for the sake of this one, rotate around the y-axis. So here we go. Not the prettiest picture. The thing is, when we were calculating volume, I would have said, hey, take the area underneath that curve and rotate that whole thing. So we were rotating a region. We were rotating a two-dimensional thing to generate a three-dimensional thing and calculating the volume. Now I'm just rotating a curve. I'm just taking this curve, which is a one-dimensional thing, and rotating it to generate a two-dimensional thing. Just the surface. It's like a lampshade or a jello mold or something like that. You're not trying to calculate the volume of jello that the jello mold will hold. We're just trying to calculate if you needed to paint the jello mold, how much paint would you need? Right? You're just doing the surface area. So amazingly enough, the way we're going to calculate that is we're going to cut the curve into a bunch of little pieces, rotate each piece around, figure out the area that it generates, and then add them all up. So zoom in on a little piece of curve here. It's a little piece of curve, say from here to there. I'm going to approximate each little piece of curve by a little line segment, just as we did when we were doing arc length calculations. Right? So that little piece, that little line segment right there, is being rotated around some axis to generate a little strip of surface area. In order to show this, I want to switch to the camera for a moment. So here's the kind of thing I'm talking about. We start with a line segment. Just think about that one edge there as being the little piece of the arc. And then you take that and you rotate it around some axis. So when I put this together here, my pen here is the axis, and that one line segment is being rotated around so that, I don't know if you can see it going down through the middle there. And the thing that's being generated is a piece of a cone. I would call it a frustum. And what I want to do is I want to figure out what's the area. If I had to paint this thing, how much paint would I need? How many square inches or square feet or square meters? How much would I need to paint it? And what I do is I unroll it so that I can lie it flat. And then I want to calculate, this is, well, how much area is there on this flat thing? So actually, I'm going to unroll it even further. I'm going to take another piece of paper here. Actually, it's the same piece of paper, as you can see. This is what I cut it out from. And I'm going to figure out the area by essentially turning this into a rectangle. I'm going to line this thing up here at the edge of the paper, and I'm going to roll it to see how long it is. So I'm trying to very carefully roll it along here, not letting it slip. The paper seems to be slipping a little bit, but I think I'm doing all right. And I say this thing is, yeah, right to the end there, and almost. So it's that long. And so there's my mark for how long it is. It's this wide. So all the way over to there. And how wide was it to start with? Right here. And so it's that wide all the way across here. And how do I find the area of such a thing? Well, length times width. Well, that width was this little bit of arc length along the curve, right? I said I had a curve, and I took a little piece of that curve. I approximated it with a straight line. That little piece is this width going across here. Let's call that ds, a little bit of arc length. Now, how long is this going across all the way around? Well, it was the length of this going all the way around this circle. Well, circle when I have it closed up like that. So it's the circumference of this circle. The axis was here, and this piece got rotated around to generate this strip. So how long is it all the way around? Well, what's the circumference of a circle? It's 2 pi times a radius. Well, in this case, the radius is the distance from, well, is it the inside radius or the outside radius? If ds is pretty small, this line segment's small, then it's not going to make much difference which side you choose. But whatever, it's the x-coordinate. That distance right there is the circumference is the radius of the circle that's being generated. So the length of this rectangle is 2 pi times x. The area of this strip is the length times the width, 2 pi x times ds. And so the total area generated for each little piece of the curve, you're taking a little line segment, and each one is being rotated around to generate the whole curve all together, the whole surface all together, that jello mold or whatever it is. Right? Each piece generates this much area. Notice that the x is changing, that this strip in here has a smaller radius than this one, out there. As the x value gets bigger, the radius is getting bigger. ds might be changing because you might, for the same change in x, you might have a steeper or a less steep. And so, if it's practically horizontal, ds and dx are practically the same. But if you get to a part of the curve where it's almost vertical, then ds and dx might be very, very different because you're going mostly upwards, right? There are changes in the y direction. But anyway, this is the little bit of area generated by that one little line segment as you rotate it around the y-axis. So the surface area is the integral from start to finish, a to b, of 2 pi x, that's the distance around, times ds. Now ds, just like when we're doing arc length, is the square root of 1 plus the derivative squared times dx. All the little line segments, each one gives you a little bit of surface area, and you add them all up, starting with x equals a all the way out to x equals b. Let's do an example of this. How about if we take just something like, how about y equals x squared? Let's say x is between 0 and 1, and rotate this around the y-axis. So this is your parabola, and we're going to rotate this around the y-axis here to generate, we call it a paraboloid, right? Now I'm not calculating the volume inside, that was other stuff. I'm just calculating the surface area. If I need to make this out of sheet metal, I'd have to figure out how much, how big a piece of sheet metal would I need? What surface area is there on it? Okay. So with y equals x squared, then y prime is 2x, and so my surface area should be the integral from start to finish. This is where my curve originated here, from 0 to 1. 2 pi times x, right? Because each little line segment, let me grab another color here, each little line segment generates one of these conical strips there. And 2 pi times x, x is the radius here, so the distance around is 2 pi x, and then the width of that thing is ds, so that's the square root of 1 plus the derivative squared. 1 plus y prime here, which is 2x squared times dx. And well, the book is very careful about what examples it gives you and what it asks you to do. It figures that you are going to do every single one of these integrals by hand. And so it's got to be real careful as to what kind of function it gives you on the inside and on the outside. I'm not so careful when I'm asking questions. I figure at this stage, you've got a calculator. You can do that definite integral on your calculator. And so when I do that definite integral on my calculator, I get 5.330 and some change here. Again, like any others in this half of the quarter, I'm more than happy for you to just set the integral up and then plug them into your calculator. In general, these integrals are pretty difficult to do unless you're very careful about what function you started with. Okay. So anyway, there's an example of surface area calculation when you've got starting off with y as a function of x and you're rotating around the y-axis. We're going to look at variations of how the curve might be given and what axis you're rotating around in upcoming videos.